All right. Hello, everybody out there in YouTube land. This is good times for all, or Zachary Zabala, if you prefer. In this live stream video, I know I usually do these in video form, but it's so much easier to do the live streams. So that's how I'm going to be doing this one in today's live stream. I would like to introduce to you the A.R.L.O.D calculator. Um, this is a calculator that I made up myself. It's just a couple equations thrown together based on the angular resolution limit and um, oh, what's the word? Perfect or right-handed triangles. Um, and yeah, this explains why boats appear to disappear from the bottom up, why the bottoms of buildings get cut off. And this would happen, this will show you that over a flat plane with zero distortion, just based on the fundamental limitation of an optical system with a circular aperture. This will show you the limitations that make it impossible to see forever. No matter how big of a lens you have, eventually the angular resolution limit will take over and distort. If you have two light sources, like think of the tail lights on a car, the further they get away, the closer they get together until finally they make one light. Now, it's not atmospheric distortions. Atmospheric distortions can cause this to happen more rapidly, more quickly, at a shorter distance. But even if it were a perfect vacuum, those two lights would still merge together and become one light due to what they call Rayleigh scattering. And this is based on Rayleigh's criterion. So we're going to get into the equation. I know at first it can look a little daunting with all the letters and, lambda, what's that? We all know what pi is. But once I break this down for you, you're going to see that this is a really simple equation that you can then use to show your friends and family, hey, look, even over a perfectly flat plane with zero refraction, zero atmospheric distortions, boats will still appear to disappear from the bottom up. This is just how our eyes work. So we're going to start off with the top equation. This is Rayleigh's criterion. Um, it's well understood. It's well established. This has been taught for uh, over 100 years. I believe this equation has been taught, showing the limitation of not only your eyes, but any lens with a circular aperture. When it has that circular aperture, it creates a diffraction pattern along your axis of sight, just the horizontal. Now, if it were a rectilinear lens, you would have a diffraction line going this way through the center and this way through the center. But because we have a circular aperture, it only cuts through the middle this way. And I still can't find a reason why. So we're going to get into the first equation, radians, which is um, another way of saying degrees almost. It's just another measurement for angles. So your radians equals 1.22 times lambda, which is your wavelength of light, over d, the diameter of your aperture. Here this is in a textbook, Rayleigh criterion. That is your symbol for radians, angle of resolution, radians, rad, equals 1.22 times the wavelength of light, right here, that's your lambda sign, over, they have it, excuse me, as b, the diameter of the circular opening, or the telescope's aperture. So the bigger the aperture, the smaller the angle you can resolve. So the bigger circle you have to look through, the bigger your pupil, the smaller that angular resolution limit is, and then you can make out two distinct objects from each other, from one another. Now, even our eye charts are based on this formula. At 21 feet, the human eye can resolve up to 2 millimeters. and that would be perfect 20/20 vision. Anything that you can resolve beyond that point, you would have better than 20/20 vision. So the average human eye is about 0 or 0.017, and they say it's a 0.02 is the average. But this is the formula or the equation you use to come up with that answer. All right, so our next one is a real simple equation. It's just converting your degrees or your radians here into degrees. People understand degrees a lot more than radians. It's just something we're a lot more used to here. So another real simple equation. So we have our number of radians by doing the first equation up here. By doing our Rayleigh criterion, we'll get our radians. Now we're going to take that radians and just turn it into degrees, something we're more familiar with. So that equals radians times 180 over pi. Here's your degree to radian measure conversion. If you wanted to go from degrees to radians, you would take your number of degrees, multiply it times pi over 180. From radians to degrees, this is the one we're doing down here. You take your number of radians and you multiply it by 180 degrees and divide it by pi. So now that we have our degrees, now this is the part where I break it into two. This right triangle calculator right here is just for really the next part. This is what I want you to focus on right now. This is why I break it into two. As you're looking out at the horizon, along your horizon line, you're going to have what is called the diffraction line. That's your angular resolution limit, when two objects get so close together and so small that you can't differentiate them anymore. They call that band right there in the middle the diffraction line. That's the technical term for what's going on. It's called diffraction. It's light interfering with each other after they pass through that opening, your pupil of your eye. So when you're looking, this center line right here would be whatever you're focusing on. That's the center of your vision. So it's going to diffract equally above and below that line. So at 3 miles, the average human eye loses a little over 5 feet. We'll just say 5 to make it easy. So then you would have this would be 2.5 feet, and this would be 2.5 feet. It wouldn't be all 5 feet or up here. It would be equal depending on where your line of sight is. So for 2.5 feet above your line of sight, it will be distorted, and for 2.5 feet below your line of sight will be distorted. That's why I'm breaking this in half. And then we do a little bit of trigonometry, and that's where this right angle calculator comes in here. So to find A, which is over here, the amount that's going to be distorted, we take B, which is our distance. We know the distance, and then we know our A, the angle that we have applied to that. And you put in a little bit of trigonometry, you find the tan, and that'll pop you out with your answer. Now to show you this one real quick, here's your right triangle calculator. And right here, to find A, the little a here, it equals B, which is our distance, times the tangent of alpha here, this angle right here. And see, it's really simple math. You'll most likely need one of the calculators, but that's it until we get to the very bottom, and this is where it gets into the elevation. So if you're standing 5 feet off the ground and your angular resolution limit is 20 feet, you're obviously not going to say that all 20 feet is being distorted from the top of the water up, because you're only 5 feet off the ground. And that would be 10 feet below where you're looking. Your 10 feet down here is above the 5 feet. So we'd cut this in half. That's why I split it up here into two. So if the observer height is greater than A, which is over here, So if you're 20 feet up in the air, but it's only 3 miles away, that would only be 5 feet. You can take that whole 5 feet and say 5 feet is being distorted of your view. Now, if your observer height is less than the amount that's going to be distorted, you will take A, not 2A, because remember we have to multiply it back together to make it the full angle. So actually, if observer height is greater than A, 2A will be unresolved, the whole amount, because we broke it in half. Now, if the observer height is less than A, which is our overall distance, or our half of our distance here, then you'll just take A, one of them, the top one here, because that is going to be distorted right here, plus just your observer height. So we'll take off that 10 feet down here if 20 feet's being distorted, and you're 5 feet off the ground, so we'll take 10 feet plus your 5 feet of your observer height. So really only 15 feet would be distorted. Now I'm going to show you, let's see, stop screen share. We're going to screen share this right here. This is neat, folks. This is going to show you that this happens. We don't really need sound, but you can see Rayleigh criterion, Brigham Young University. They have a laser set up here. It's going to be going down a hallway, and right here you see he's got the two lights. Oh, let me open this up a little bit more. So it's going to go down the hallway, and it's going to look at these two laser beams, and what they have here is an aperture that they can change the size of the aperture. You'll see it here in a second. It's a real quick one, minute 20. These are my favorite videos. They don't mess around. I'll put the link in the description if you want to check out this video. I know this is on our How the World Works. I've used this video multiple times. Yeah, these are just great little demonstrations to show you, see how the aperture size is opening and closing. Now this is the part I want you to focus on. See, we have two separate dots here. But as she closes this aperture, look what happens to the dots. They merge together and become one. And then as she opens the aperture back up, you'll be able to see both distinct dots again. So she's going to measure the size of the aperture and say, this is the limit where you can make out the distinction between the two dots. We'll go back here. See the distinction? We have two dots here now. But as she was closing the aperture, watch what happens to those two dots. They merge together and make one blob, one round blob. So they were looking for the angular resolution limit to where you could distinctly see the two different dots. Love these videos. I just love them. And then a little presentation, well, not a presentation, but just a demonstration on to show you why this makes the boats appear to go over the curve. It's not the great, I'm not a great drawer, folks. Hold on, let me see. Whoops. Cancel that. I know I have it open. Okay, we're just gonna have to share screen. Here we go. Okay, so as you can see, we have our little person out here at the beach. We have our water, we have our skyline, and we have our sun, our boat. Now this purple line is the angular resolution limit. This is your diffraction line. As you can see, it's an angle, so of course it's going to get bigger. Now this isn't to scale by any means, but it's going to get bigger the further out it goes. That's how angles work. So what we have here is our boat. And as you can see this guy, he can look and he can see the bottom of the boat, he can see the sail, he can see the whole boat. It's nice and close. Now, as we scoot this boat away, you can see the bottom is getting harder to see and make out. There would be like right in between here, you might see the bottom a little bit, but like where the mast and the sail are starting to meet, it would start blurring together. The image would start distorting a little bit. And as the boat moves further and further away from you, now this isn't changing the atmosphere or anything like that. We could say this is even in a vacuum. Now, once it gets to this point, you can see that he can no longer see the boat touching the water in the bottom. Even though he's in the same spot, the visual, there's no refraction, there's no anything like that. We could say that it is a perfect day, not a particulate in the air. The temperature is exactly the same. There's no weather distortion going on at all. Just by the optical limitations of any lens, not just your eye, but a camera, a telescope, any lens with a circular aperture, you will start losing the bottom of the boat first. And you will only see the sail here. Now, all of this is going to turn the boat, anything within that field of view, is going to turn into the most dominant color. That's why we always see it as sky. Even when you're going up over a highway, and you get right an angle with it and you see the highway kind of turn into the sky, but you can see the guardrails and the grass on the sides, and they look like they're going up all the way to the top of the hill. But the road right here will look just like the sky, even though you know that road is asphalt. It's not the color of the sky, not even close. It turns into the color of the sky because that's the dominant color that you're seeing. When you have that right there in the center, there's a lot of different colors down here, but that color up above is dominant, so it's going to take over the color of the asphalt. And it turns that asphalt the same color as the sky or whatever's behind it. It can do it, it can make it look green, whatever's behind it, it kind of mirrors that. That's why we see birds being able to dive into the water, it appears like, but really they're just going into that diffraction limit, which is, it's all dependent on how you're looking at it too. If you're pointing down a little bit, it might be the water that takes over. If you're pointing up, it'll be the sky that takes over. So it all depends on which is the most dominant color that you're seeing will determine what color your diffraction line is. So right here, as you can see, we see a lot more sky up here than we do water down here. So the boat would kind of look like the sky. And then you would have your water line somewhere right here in the middle, because that diffraction line's gonna, it's amazing how it happens. So yeah, that's pretty much it. You can see as the boat comes towards you, it looks like it's coming up over a curve because you're seeing the sail, more and more and more of it, and then you finally start to see all. And again, this isn't to scale, folks. It'll act a little bit different, but this is just like a rough showing you that just that limitation of your eye will make everything. We could draw, let's see here. We'll just draw. You could have your building right here coming up out of the water. Oh, we're going to do this. Oh, come on. Doesn't need to be perfect. And you can see the whole building, right? And then we come up over here and we draw the same height of a building, kinda. And you can see that almost the bottom half of this building is cut off. This one, you can see the bottom here. Maybe somewhere halfway up the window, and I found lots of pictures like this where you'll get this squiggly line going all the way across the skyline. Like you'll be zoomed in on a building and like a couple rows of the windows will be more distorted than the rest of them. That is because you're getting a clearer view of the bottom of the building and the top than you are of the center right here due to diffraction. But as you can see, as you come back here, the whole bottom of the building's cut off and it would look like it was over the curve. And that's going to about wrap this live stream up, folks. I didn't want it to be too long. I want people to be able to click on it and actually watch the whole thing. But this is, again, we will show it one more time in case you're just getting here a little bit late. But this is I'm looking for a better name. Someone told me to name it after myself, but I can't do stuff like that. But the R.L.O.D calculator, I thought it made sense. Angular resolution limit over distance. Um, Pretty easy to remember once you remember angular resolution limit, and then you just add over distance. But yes, the angle, not refraction. Now, this is diffraction. If you go into my playlist, there are, I think I have 30 some odd videos with tests and demonstrations I've done myself um, showing this. And diffraction and refraction are a little bit different. Refraction happens out in the atmosphere into what you're looking at. Diffraction takes place in your eyes. After that light that you are gathering passes through the iris, your pupil, that's your aperture. Once it passes through that aperture, the light diffracts into each other and it creates this band. This is well um, established physics. It's based on Rayleigh scattering. We get Rayleigh's criterion equation out of this. Um, but yeah, the angular resolution limit, if you go look up diffraction, diffraction, diffraction. Um, and it even happens, it's not just at infinity. There's two types of diffraction. There's Fresnel diffraction and there's Fraunhofer diffraction. Now we are speaking about Fraunhofer diffraction. That's when you're looking off into infinity beyond your angular resolution limit. Now Fresnel diffraction, um, say you're looking at a tree, you know, real far away, and you see the green on top of the tree, and you know that those are leaves, but you can't make out an individual leaf. They're too small, they're too cram packed together, so all you see is green. But you know it's made up of a bunch of small little different green things that are outlined and have lines in them, but you can't see any of that. That's Fresnel diffraction. You can also think of it as looking at your hand. There's little cells that make up our skin, right? Well, the average human eye can't see that small. So when you look at your hand, even though you see the whole image right there in front of you, the lines on your hand are so small and drawn together that you can't differentiate one from the other. That is Fresnel diffraction. That happens all the time, always, no matter what. And Fraunhofer diffraction, that's when your angular resolution limit over a long distance comes into play and actually distorts an image so out of touch that it makes it look like it's, going over a curve, for example. Those are the two differences. So I am going to get out of here. Thank you all for joining me. If you could share this around, this is something that ballers have to add to their curve calculators. The Earth curve calculators that they have to add this on top of it because this is a fundamental limitation of any lens with a circular aperture. And the human eye at just, it's really interesting, the human eye at just 3 miles, they say that's as far as the human eye can see out over water. And then it starts going into the curve. Well, at just 3 miles, it's 5.5 feet that will be distorted. So if a boat is 3 miles away from you and you're sitting there on the beach looking at it, 5.5 feet of that boat will be unable to differentiate one of the light sources coming off of it from another. You have a black line, that's a light source. You have the white next to it. You have some letters. Those are all considered different light sources. And when you get too far away, they all kind of merge together into one light source. And eventually the whole boat will merge with the rest of the background to make your diffraction line. So this is how our eyes work. This is why boats would appear to go over a curve even in perfect weather when refraction is not affecting the outcome. Or if it is, it's very minute. But the angular resolution limit over distance calculator should have to be added to every Earth curve calculator as another amount of distortion that should be taking place. So if you're looking at a lighthouse and it's so many miles away, you would say, oh, the Earth curve calculator this. Well, yeah, we still see this much of it because of refraction. Then you go and say, okay, well, you're going to have to erase this much more of it, of what you're seeing, or actually add to it, because this is going to subtract. So this is the amount that you would need to add to that building and say, actually, well, this amount is still there. It's just being diffracted from our view. So yeah, this is a one of those things that they can't get around. It's a fundamental limitation of all lenses with the circular aperture. Now, yes, of course, if you get a super zoom camera and your aperture is much bigger, you're going to be able to resolve things at a much further distance. This is why when you pull out the camera with the bigger aperture, you can see the boat again. Whereas with just your eye, your pupil is so small, you weren't able to resolve that boat. It was beyond your angular resolution limit, and diffraction erased it out of your vision. So there's a big difference between refraction and diffraction. Refraction is more of an atmospheric phenomena, whereas diffraction takes place inside of our eyes. One more time, here is the equation. It may look a little daunting at first, but these are really simple equations. You can find online to do for you real easy. I know for sure there's a Rayleigh's criterion calculators. They're used in photography all the time and for astronomy. Degrees to radians, that's a real simple one. This one, of course, is just dividing it by 2, breaking it in half. And then this one, there are calculators out there for this one as well, a little bit of trig. But I'm hoping with a little help from some of the people out in the community, maybe we can put together a program to where you just punch in your distance and you could have like human eye or P900, P1000 already programmed into it. So you would just have to go in, hit a couple buttons, hit in your distance, and it would tell you how much will be distorted. Now, again, this is a minimum. This is the limit. Any kind of atmospheric distortions will only make that angle, that diffraction angle, larger. So that's where I quit, because telling what the atmosphere is doing over a 10-mile distance, even the greatest engineers and stuff are having trouble doing this accurately. So I kind of quit once the equations had every letter in the alphabet and were like 10 lines long and 20 characters wide. I was like, okay, I'm done. I'm not learning all that. And they'll even say that they're not very good at it yet. So that's why I stuck to this, a phenomena that happens inside of the viewing apparatus. It has nothing to do with out there and what is being distorted from all the other things that could be taking place. This is simply a limit of our viewing devices, you could say. Your eye, a telescope, a camera, all these things have limits. And this limit can be turned into a curve, if you will. And that's going to do it. I love y'all. Thank you so much. Please share this around. This is definitely something that the Globers can't get around. And they need, I don't know what they're going to do about this, because we've brought it up to them before and they kind of just ignored it. But I think if people start pushing and asking this question more, they're going to have to try to come up with something. And I think it'll be fun to watch them squirm trying to do that. So that's it, folks. I'm going to get out of here. I love y'all. Thank you so much for joining me. This is Good Times for All here, signing out. As always, thanks for watching.